Okay. All right, guys. So welcome to welcome to another lecture in 102. All right, guys. So let's at least review what we did last time with the reflection, refraction, Snell's law, and everything. Okay, using the equation that's given there, calculate this one. So this one is pretty much exactly the same as before. Okay, except of course it's just maybe just different orientation on and on. But I can say that this is probably going to be the hardest type of question that is going to show up in the exam. So, all right, everyone try this. And I think of it like a mini quiz here. All right, so I think I can remove this part here. All right. All right, here we go. Oh, did you break anything? I hope not. All right, guys, try this one. And I hope it's okay. All right. So in the figure, you have a light ray enters a glass slab at a point A, which is on the top, with the incident angle given to be at 45 degrees, and then undergoes total internal reflection at point B on the side. All right, what minimum value for the index of refraction? They want you to figure out the N value of this material of the glass can be inferred from this information. All right, so give it a shot. What do you think? All right, so once again, just a quick reminder. So what we have here is, okay, you have the refractions happening at point A, all right? Plus, because you say you want to figure out just the value that is just enough, right? Just the, okay, all right, if you can have the glass to be at this particular value of N, then you will be able to get the total internal reflection. Once again, if you want to talk about the like a boundary between you want to cross over from having reflection or not, that means you just need to set the outgoing ray to be at 90 degrees. Got that one? Okay, that is sort of like the condition that you're going to get it or not. So with that, don't forget every time that you are thinking of trying to apply the Snell's law, you draw a normal line. All right, just to make it clear there. Okay. All right. So let's start from the top, shall we? So let's say at A, once again, just a quick reminder, N1 sine theta 1 equal to N2 sine theta 2. That's the Snell's law equation that we always use. So in this case, light coming from the air entering the glass. Okay. So what you can say is at A is going to be N of air. And then sine of, they said is 45 degrees. You just plug that one in. Now you enter the glass. Let's say that the glass has the index of refraction of N. So you just say, okay, it's N. And then sine of, all right, you don't know what it is. So let me call this alpha for now. All right, because you don't know what is going to be the refracted ray. So you put it as like an alpha for now. Okay. All right. Anything that you know the value, if you like, you can plug in the value if you want. So N of air is 1. Okay. And a sine 45, you can put like square root 2 over 2 on and on. But it's still two unknowns in this equation. It's N and the alpha. That's fine. You leave this one as an equation number 1. Then you move on to another point. So you say, okay, John, there is another things that we can analyze, which is what is going on at point B. So you move on to point B and apply the same thing, Snell's law. So at B, light coming out from glass to air. So what you can say is it's going to be N of glass, which is N. And then you are hitting this point B with the incident angle equal to that blue angle over there, which you can say, well, John, that's no big deal because this is a right triangle. So if we already assumed that the top angle there is alpha, so we know right away that the incident angle for point B is going to be 90 minus alpha. You guys with me? All right, so you can put sine of 90 minus alpha there if you want. And then you equate that to outgoing ray is entering the air, so you put in air. And then because you set everything to be at 90 degrees on the way out, right? Because that's a condition that you want to check. There you go. Put 90 degrees there. All right. And this is going to give you n cosine, because sine 90 minus alpha is cosine, equal to n air. You can plug in 1. Sine 90 is also 1. So this means it's going to be 1 on the right. And this is going to be your second equation. And from these two equations, now 2 equations, 2 unknowns, you can solve for n and alpha. Cool? All right. So if you have calculator on hand, pretty much, the equation number 2 will automatically, well, not automatic, but I mean, it depends on how you want to get to the end, but for simplicity, maybe you can take 1 and divide it by 2 first, if you want. I mean, because if you have your calculator on hand, by doing the division between these 2 equations, n will cancel, and you get 10 of the alpha equal to √2/2, something like this. Okay, so I mean, it's sort of like you figure out what is the value of the angle alpha first. And once you punch the calculator, got that numbers out, and then you plug it back into either one of these 2 equations to figure out the n. Okay, but if you want to be like a little bit more sophisticated, if you like, what you can do is, well, John, I just want to jump right ahead into the value of n. What you usually can do is, or using the identity sine square plus cosine square equal to 1, right? If you want that, that will be fine too. Okay, so if you want to, bypass the alpha calculation, you don't want to punch the calculator, you can just say, okay, John, I can know this, that sine of alpha is just sine 45 over n, plug it in. I know cosine theta from this equation is 1 over n, you plug it in, and then you can solve for n this way as well. Okay, right, either way. Okay, but I mean, it's just 2 equations, 2 unknowns, whatever you like, it's fine. However, I know, I mean, using calculator is much easier because otherwise then by eliminating the alpha, you have to deal with the n square, stuff. And then, I mean, it's still messy anyway. You still have to rely on calculators no matter what. So maybe just, calculate the alpha first, and then we'll just got the n afterward. That will be cool. All right, guys, but I think this is a very good sort of like example showcasing how to utilize the Snell's law equations and what will be the conditions that you're going to have to meet when you are analyzing the total internal reflection. Okay, any questions so far? Cool. All right, so if not, guys, good news, last topic of the second module, it's done. I think it's been a long way, guys. I mean, think back about what we have been doing. It's quite a lot because we started out from oscillations and then we get to the waves. Once you get to the waves, we give you 2 examples of waves. It's a light wave and the wave on a string, maybe, or water or whatever. And then we now at the last stop of the light, okay, which is now we kind of like threw away all the wave descriptions, but we only going to look at, once again, just like we started out this particular handout, we only care about the direction of the motion of the light. Here we go. All right. So we are going to use rays, right, to identify the movements of the light. We only care about the direction of motion, right? So we don't care about the fine detail of the sine and cosine, the oscillations, the 2 variable functions, on and on. So this is where this figure is going to come into play today. All right. So now we are going to trace where the rays go. And eventually, these rays will end up someplace that you can observe. Okay. So this topic is about the image formation. All right. So we are going to do the image formation now. So when we talk about the image formation, there are 2 devices that we are going to take a look at. And these are the main 2 devices that you are going to pretty much like, you have already experienced this all the time. First is lenses. So lenses or the transparent material that you make it in a curved shape a little bit. And then by utilizing the refraction of light, then the light path will deflect it, and eventually they're going to cross at some point. Okay, all right. So this is how you are generating an image, because at the point where those rays intersect, that can be an image, because you already copy the information about the source of the light on one side, and you pretty much regenerate that on the other side. You guys with me? So that means whatever information is on the left coming from the source, it's pretty much like, okay, I got the lens, and those lenses somehow redirect the light and make them meet again. So you kind of like reproduce whatever is going on from the source. So we call this an image formation. Okay, so that's why the key factor of this one is you need the intersections of the ray to generate an image. However, because this comes from the real intersections of the ray, we call this a real image. Where have you seen the real image? It is right now on my hand, right here. That's real, right? Because the light from the projector actually gets deflected, everything, and then it's about to, it's focusing, right? It's focusing down. Well, okay, it is focusing down, and then I'd have to update someday. Right? It's focusing down onto, when they say, hey, in focus, right? Because sometimes when you move things around, you do the focusing of the lens, the image on the screen might be blurred a little bit. So that means the intersection is not perfect. But once the image is perfectly clear to you, that's exactly the perfect intersection of all those rays. And it's real because I can put my hands there. It's on my hands. I can grab it. I can put it on screen. That's fine. So this is real image. Cool. But on the other hand, there is another kind of image that you actually looking at it almost every day. I think you look at it, you know, you look at yourself in the mirror, and you know that you can see your own image behind the mirror all the time. However, that kind of image, you cannot interact with it. You cannot grab the figure. You cannot grab your own image. You have nothing. You cannot do anything behind the mirror. And this is what happens. Mirror reflect light. So that means once you have a light source, and then the light coming out from the source in all directions. So once it hits the mirror, it's just following the law of reflection, right? So it's going to get reflection, reflection, reflection. So if you look at the ray of light on the way out, can you see that the ray is diverging out? See, right? So when they are diverging, there's no way that this ray is going to intersect each other. So that means on this way out, no way you're going to generate any real image. Forget about it. However, if you put your eyes there, so this means if I place my eyes here, our eyes, in cooperation with the brain, whenever the light hits you, your brain will interpret that the source of the light coming from, hypothetically, right there. Your eyes cannot distinguish, is that real or not real, but that's what you can see by your brain. So when you have a diverging rays of light hit your eyes, your brain will interpret that the source of that ray comes from here, right there. But because this source is pretty much imaginary, it's not there, it's not real. So we call this a virtual image. Cool? All right. So the image that you're seeing yourself in the mirror is a virtual image. You got those light rays, which is diverging. So they are not intersecting. So when they are not intersecting at all, there's nothing that you can do with those images. You cannot grab it. You cannot put those image onto like a CCD camera. You cannot capture it. No, you cannot do anything. The only thing that you can do is just looking at it. I mean, you can take a photo if you like, doesn't matter. But I mean, you cannot grab it. You cannot put a screen behind. No. All right, guys. So I hope this pretty much conclude the classifications of the image that you can form. There are only two types. It's either real or virtual. And the way that you can classify this one is easy, looking at the rays of light. If they are crossing with the real rays, there's a real image. If they're not, you have to extrapolate by yourself. See, by using those dashed lines and other stuff is not actually intersecting themselves. That's a virtual image. Cool. All right. So once you understand these two types of images, the only thing left for you is just try to apply those law of reflection and law of refraction and try to figure out where the rays goes. And that's it. That's how easy it is. For example, look at this one, guys. This is how simple things are. All you need to do is just draw light rays. And if it hits something that reflect, you just do the law of reflection. If you hit something that have a refract, you just do the refraction. And then you just trace the rest of the path of these rays and see where those rays go. For example, once again, we redo this light reflecting the plane mirror. As you can see, once you get the reflection, the ray is diverging, and then that's your virtual image that you see yourself in the mirror, all right? Something like that, right? So things will get more interesting later, but just to make the terminology click and kind of like obvious. So that means what you can do is if you place an object, so we're going to use O for that. So when you have an object placed in front, okay, when we say in front, you only have a single mirror or single lens. So whatever the object is, that's the front, okay? So this is the front of the mirror. The distance that you measure from the object to the center of the mirror, we call it an object distance. Yeah, easy? All right, yeah, that's an object distance. And whatever image that happens after this, which in this case is easy because of the law of the reflection, the image that show off in the back will have the same distance in this case, right? But it doesn't matter. The distance from the center of the mirror to the image location, we call the image distance. Done. Okay. All right. But this is not very interesting, Matan. This is like, okay, it's kind of boring. So it's going to get more interesting when the mirror itself is curved. All right. What kind of curve image will do to the rays, guys? So this is kind of like we're going to have a lot of fun today because it is geometry. ไม่รู้สนุกมั้ยนะแต่ดูนักเรียนน้อยลงเรื่อยๆถ้าจะไม่ค่อยสนุกกับคอร์สนี้นะ อาจารย์ไม่ค่อยแน่ใจแต่หลังๆนะตอนที่อาจารย์สอนคลาสที่เป็นอีกคลาสหนึ่งนะตอนแรกอาจารย์ก็สอนแบบไม่มีอัดวิดีโอโหคนเต็มคลาสเลยพออาจารย์เปิดออปชันบอกว่าไม่ต้องห่วงนี้อาจารย์อัดวิดีโอคนหายไปเลยโอ้อาจารย์ว่าพวกเราก็โอเคนะอาจารย์ว่าเอาจริงๆนะอาจารย์ว่าสอนออนไลน์ก็ not too bad นะหลังจากที่อาจารย์มีไอ้ sound effect thing to play with เนี่ยอาจารย์โอเคนะคือไม่ค่อยเหงาอะไรนะเล่นกับตัวเองไปเลยนะถามเองตอบเองเฮ้อฮะโบ๊ะบ้าเลยนะokay guys, so what is the curve mirror do to the rays? Here we go. Because it could be any curve. So in general, well, adan, we don't have to pick some curve, right? If it's just any curve, then we are go crazy, right? Because I mean, it could be any curvatures and other stuff. So we are going to focus on the spherical type. The reason it's spherical because of course it's easy. We have like, you know, it's a very nice symmetric shape and you have the center of curvature all the time. A single curvature, I mean, the single center of curvature, single point, okay? So that's a center of your, think of it like a circle. That's a center of circle. Now, if you send in the light horizontally, hit the curve mirror, which is a spherical curve, then by the law of reflection, guys, what do you think it will happen? Majan, don't forget to draw this. There we go. Normal line. Okay, let me zoom in a little bit to make it clearer here. I can draw the normal line, right? But if I draw all the way to the center, it has to be, this is it. Everyone knows the line that drew from, that I just drew from the center to hit the circumference of a circle will be exactly cut this angle in half. You guys with me? Right? Because every time that you hit the circumference with a radial line, you get a perpendicular hit like that. All right, so it's perfect. So that's following the law of reflection automatically. So what it means is that rays of light eventually is going to hit this point down here, which, all right, you start to think, that point has to be half of the radius. With me, guys? okay, because of the law of reflection is half the angle. All right, so that means if the radius of the circle is r, then that point F must be located at half the r. But then, wait. If you do this symmetrically, so you send in another wave in the bottom, there could be another wave coming in the bottom, hit the mirror, it's gonna bounce back and hit that point F as well. So that's why this is the place where we're gonna call this point F the focal point. Because this is the point where once you send in just like a ray of light or a beam of light, bam, this beam of light will get concentrated into a single point right here. Okay, so we call this a focal point. And now we know from the geometry that we just discussed, this focal length, right? The length is the distance from point F to the center of this mirror. It's going to be half of the radius of the curvature automatically. All right, so this is it. This is pretty much the whole business of this reflection from a spherical mirror. That's it. That's all you need. All right. And you can do a little bit more by what if the curvature go opposite direction? So instead of having the curvature going to your right, now it's curved to your left. So this case, we're going to call it this is a convex mirror. The other one is called concave. Concave is like wow, right? It's concave, but this one is noon all, right? So it's convex out. So this one, the light are coming in, you still follow the same law of reflection, but because now it's reflecting out. So now the outgoing ray is diverging. You guys with me? But it's going to diverge in the direction that if you trace out that line, it's going to cut somewhere virtually, of course. So with that, then we're going to call this another focal point as well for this kind of mirror. But now you can see, this is not real. This focal point is sort of like virtual because it happens behind the mirror. Okay. But anyway, we're going to call focal point anyway. So this is it. The geometry looks exactly the same. The focal length is still that distance from point F to the center of the mirror. So this is still half the radius. So that's why we got this easy connections between the focal length F and the radius of curvature R. It's just half the radius. That's it. All right, very cool, guys. Almost done, almost done. So if you kind of like, okay, Dan, I can see it. What is going on right now is just the reflection. But whatever happens in front of the mirror is real. So just give you an idea, this is what we're going to do next. All right, later when we really do the calculation. What is happening on the left side, which is the front, we call this a positive. Let me put like a big positive sign there. And anything that go virtual, which is, behind the mirror, no, it's not going to happen. Lights never travel behind the mirror. This is going to be the negative side of things. Cool. All right. So this will help us do the actual calculation after doing just the ray tracing at this point. Right now, we're just tracing the ray. So I'm like, okay, see this, see that, using the ray and the directions of those rays after the reflection. All right, guys, keep going, keep going. Things still, kind of having fun here. All right, now let's see if you can relate this to what you have experienced before, maybe here. If you have seen like I don't know how to call this properly, but I think this is like a makeup mirror or something, right? When you have like a curved mirror and then when you put your face in front of that one, your face get like magnified a lot, right? And it's easier for you to deal with your face and all this stuff. So that is a kind of the concave mirror. And now your image will appear bigger. Why? Here we go. Okay, look at this. This one might look a little weird. I think I must have placed different figure here, but it works. It works. Okay, guys, follow me a little bit here. So here we go. So I place. Let me say this is my object. Sorry, because it's opposite to the figure that's showing. So let's say this is my object. So this is your face. All right, your face is right here. So let's say there is like a point on your face that you want to look at. Think of it that way. All you need to do is just trace the rays coming out from this point. So one thing that you already knew, Ajahn, I saw what you did before. If you have a light that going horizontally hit the mirror, it's gonna bounce and going through the focal length. You guys with me? There you go, right? The green line, cool. Okay, but now, because this is coming out from a point, it's not like a parallel ray on it and a beam, just like what you did before. What else can be determines the direction of light? So all you need to do is just draw another line, the line that you know exactly what is going to happen on the surface of the mirror. I can draw this one. Think about this, guy. If I have another ray, look at the blue one, that go out and hit the mirror perpendicular to the surface of the mirror, what will happen to this ray? It's going to bounce back on itself, right? Because you hit everything perfectly 90 degrees. So that ray, the blue one, will just bounce back and go up here. That's the blue line. Yeah, no problem. So now you can see that the green and the blue already intersect at that point. So you can actually stop right here, but I don't need to do anything further. This is it. My conclusion is this is going to be the place where the image is formed. That red, blue, the red big dot right there. And this is the reason why you can see that, that's why your face look bigger, because look at the object. The object is this big, but the image is this big. See that? You get the magnification out of it. All right, that's the whole business of trying to figure out the image. This is your object right here. It's this tall. Once you do the reflection after this, okay, it's bigger. Okay, and this one is it's an actual intersection of the rays. So this is a real image. Cool. All right, so this is how it's supposed to be done. Okay, but then wait. This is not this case, because what you just saw on that cosmetic mirror and all the stuff right there. Wait a second. The figure that you're seeing over here, the image supposed to go behind the object. With me? So if you place an object here, the beam of light will intersect behind the object. That's not this case. You guys with me? All right, guys, I want you to try. How can you get to this image right here? Is this image real or virtual? What do you think? The one that has like your face blow up like this. Is this a virtual or real? What do you think? Yeah, it's supposed to be virtual because your face goes up behind the mirror. Anything that goes behind the mirror is not real. Light cannot travel there, right? But my question is, how can you adjust starting from this idea, all right, I kind of get it. The way that you want to get to the image location is looking for the intersections of the rays. Any two rays will do, right? That's it. All you care about is just only two rays. And once they cross, bam, that's the image location. Find me the location where you will get this virtual image that is blown up. All right, guys, give it a shot. ให้คิดแป๊บหนึ่ง สนุกไหมอันนี้ไม่รู้อาจารย์รู้สึกมันสนุกดีนะ It's more like a game playing. It's not like a อาจารย์มันยังไม่มีอะไรคำนวณเลย Right, not yet. All right, and here we go. So for those of you that can sort of like right now thinking about it, thank you for ทำเหมือนคิดนิดนึง Okay, very good. เป็นกำลังใจให้อาจารย์ บอกไม่ได้คิดอะไรอาจารย์รออาจารย์เฉลย All right, think about it, and then sometimesอาจารย์ it's not easy because if I can do it probably, with some rulers, pen and pencil and stuff, I can draw it. So it's probably easier to just do simulation. All right, guys, go back to that ophysics.com once again. Okay, and then now we are going to go forward and look at the light category there. And there are, once again, a couple of things that we can look at. But the one that we are interested in right now is, here we go, convex and concave mirror simulation. Here we go. All right, there you go. Am I in? Oh, it's loading. All right, okay. There you go. All right, so in reality, you use software now. You're not going to do it by hands, of course. All right, so this is something that you can play around, and I think it's much better to do this. All right, this, if you want, all right, you can go to this websites right here if you want to follow and want to play around with it. It's allphysics.com, and I think it's L10.html. All right. So if you want to try on your own notebook or your tablet. All right. But the key idea is this. See, so this software or this simulation already give you pretty much everything that we need. And you can move things around by just adjusting the object location over here. See, all right. I can move the object around and you can see where the lights travel. You can also change the focal length of this by adjusting the focal point of the mirror. All right, and just to make it clear, I mean, you can increase the height of the object, lower the height of the object, on and on. Cool. All right. So the case that we just did, it was just like I have the object upside down, place it somewhere here, and you can see that now your image is behind the object. You guys with me? Right? This is exactly what we did. All right. So we have an object placing somewhere around here. You draw the line. If you have the horizontal ray, the beam will reflect through the focal point, bam, going that one. And then you just need one more line. It's this line right here going radially. It's going to go back on itself and it cuts right there. So you know that's your image location, right? This is what we just did. Okay. But now the case that you see yourself have your face blown up in the mirror is when, here we go, you have to move your face close. See? So this is happening. If you move your face closer to the mirror, your image will appear, well, it's not appear to your eyes because this is a real image, but the real image will go further backward, right? You can see that, right? It's going backward. But now, once you have your face closer than the focal point, can you see that? Here we go. Now it's appear on your right side. So this is happening when your object location has a distance closer than the focal length. So that's when you move your face closer to the mirror. This is what happened, guys. Yeah. See, the reflection that coming off from this is now diverged. So they're never going to cross. Okay. But if you put your eyes here, your brain will tell us that, hey, the source coming from there. So that's why you can see your face bigger. Okay, got it? All right, the height is bigger than the original, and that's your magnifying image right there. Cool. All right. What I know. So yes. Correct. That's a very good question. In reality, it has to be two-dimensional reflection. So that's why, yes, in reality, you have to do that. So you have to do x-axis, y-axis. Actually, you have to do all directions. Yes, very good. All right, but I mean, we assume the isotropic properties of the whole mirror. So I mean, you can rotate this one, you know, around the x-axis. You generate a dome or like a curved mirror like that. Yes. All right, I think that's have a very, very good implication to reality as well, because in reality the image might not be that perfect, right? Yeah, I'm sorry, the mirror might not be that perfect. Yes.
When the ray reflects, like, does it have to go to focal point for ray, or
depend on the direction of that ray? The ray that's gonna hit the focal point is the ray that go horizontally. So if focus on this one, it's this ray right here, the one that go here, reflect, and it's gonna hit the focal point. See that? But if you look at other rays like this one hits the mirror perpendicularly, so it's gonna reflect on itself, something like that. So each ray will have its own law of reflections applied, and then it might not hit the focal point all the time. Yeah, it depends. Yes. All right, guys. So I hope this will help in terms of like you can play around with this. And then I can flip this into a positive focal point. And then I can do a lot of stuff. Okay, what is this, a concave? Here we go. I don't know what's going on here. Where is a convex? I think I can do convex, but just I thought I can flip this around to the other side and we go convex, but there's no I mean, the mirror is gone. But anyway, so I hope this one helps in terms of like allow you to play with the location of the object, okay, or the focal point of the mirror and all the stuff. It's kind of fun to play. All right. But it's still, we want to calculate, right? We don't want to just play with this and then, try to come up with the location of the image. All right. So that's what we're going to do eventually. All right, guys. So I hope this simulation works. And you can understand now, if you have the convex mirror, the one that you see at the street corner, yeah, the one that you don't have to look at the other side of the other end of the corner and stuff like that. So it's the diverging mirror, right? And if you look at the trace of the bray, now you understand what is happening. So when you look at this, the object is in the front, then you generate an image behind the mirror, so it must be virtual, but then the size is reduced. That's why you see whatever the image that shows up on the mirror to be smaller. It's squeezed, yeah, and then all this stuff. All right, cool. All right, guys. So I think this is give you a very good background of what is about to happen next. All right, I want to calculate it. I don't want to just draw the rays because you can use software for that. So what we really need, all right, I'm just going to introduce to you these two equations. So we'll take a quick break. Sounds cool? All right. So the first, and it's a very simple equation, is this one. Let me put like a 1 star there. If you want to find the magnification, it's easy. If you want to know the final image is bigger or smaller than the original, all you have to do is just take the size of the image divided by the size of the object, and then you're done. But this one is not so good. The reason I say it's not so good because it's pretty much like absolute sign. So I kind of like, I want to cross this one out because it's not very, very nice in terms of like a real application in your determination of the image location. The one that I like better, and I think it's kind of like complete in itself, is this one. So actually, you can also calculate that magnification M by knowing the distance of the location of the image. So if you know the image location, and if you know the distance of the objects, right? All right. So that means you can take the image distance divided by the object distance with the negative sign, guys. This is very good. If you know this, take the negative sign along with you. You will be able to tell is the image is upright or is inverted automatically after your calculation. It's very good. All right. So don't only take just the size of the magnification. Take the sign along with you. You will be able to tell if your final image is right side up or upside down. Okay. All right. I will show you with examples. It's easier to look at it using examples. All right. But at this point, let's say, all right, we have some rules that we can follow. And after that, everything will be pretty much streamlined and very good. Second equation that I asked you to pretty much like consider is this one, guys. Equation number 1. Right there. We call this the mirror equation. And when you look at this equation, it's very easy to use. It turns out all those terminology that we defined, the image distance, object distance, focal length, they are all follow this simple equation. The 1 over P, 1 over Q added equal to 1 over focal length. อันนี้ไม่แน่ใจเคยเห็นมาบ้างไหมนะ All right, but if not, this is it. This is how easy it is. The only complication of using this is just you have to assign the correct sign. That's it. That's the only confusion that can occur in this kind of problems. All right, like when you're going to use the positive sign, when you're going to use the negative sign, or after your calculation, you get a positive numbers. What does it mean? If you get a negative numbers, what does it mean? Something like that. All right. And even though the textbook will give you like a big tables of the conclusion of it's positive when here, when there, and seems like, well, do I have to memorize this stuff? It turns out no, right? I will have a very, very easy rule of thumb that once you follow that rule of thumbs, well, everything is obvious, okay? So I will show you how to solve this problem after the break. Sounds cool? All right, but you can read this one through just in case if you want and play around with the simulation during the break if you like. Maybe not. All right, guys, so take 10 and then we'll come back and solve this one. All right, it's gonna be fun. All right, guys. Let's see how can we do this calculation. All right, the good thing about this one is once you understand how to do the mirror, lens business is automatically done. It's kind of cool. All right. I don't know, have you seen this kind of conclusion before? But to me, if you kind of get how to utilize that mirror equations, it turns out the lens equation is exactly the same. Amazingly. All right, guys. So you have a concave spherical mirror with the radius of curvature given. All right, so you can say this is R, then this is it. All right, R is 20 centimeter. Find the location of the object distance, the image, right? Because you already know. All right, so let's say, hey, part A, your object location is 40 centimeter. Okay. Now your focal length has to be half of the radius. So that means it must be 20 over 2 and it's going to be 10 centimeter. All you care about is what is the Q. See, it's done. Okay. The only thing left is, well, now wait a second. You have a concave mirror. So there must be two different things if you have a concave or you have a convex mirror. Okay. And that is in the sign. So come back to this page just a little bit, guys. This is your concave mirror, right? Look like this. The bottom one is a convex mirror. And sometimes if you kind of like confused between like convex or concave, which one goes which, you can call the first one is a converging mirror, the one that converges the light. Okay. And the bottom one you can call this a diverging mirror, the one that diverges the light out. Okay. All right. But we already discussed, well, you call this a real focal point. Because the uppercase, the light, once it gets reflected, they are really intersecting each other. So whatever that's real, we're going to call this positive. So that's why we can do the conclusion that the focal length of the concave mirror is positive. And by the same arguments over here, in the convex mirror, the focal point is behind the mirror, which is not real. So that means you can draw the conclusion that this location over here, which is the focal length, you can call this is a negative focal length. See? All right. So by understanding this terminology and the agreements or the convention about the sign, you are almost done. Come back here. So what you're saying is, Ajahn, this is a concave mirror. It's a positive 10 centimeter. Okay. And Ajahn, what about the sign in front of the object distance? You have only single mirror. The object is in the front. So it must be positive. So no doubt, in that case, you always have positive object distance all the time. How can you place an object behind the mirror? That doesn't make sense, right? So that's why, all right, they're both positive. So that's it. Try 1 over P plus 1 over Q equal to 1 over F. Plug in the value that you have already known. It's 40. Let me omit the units. Just use the centimeter. You don't need to convert them because as long as you use the same units on all three terms, you are fine. Plus 1 over Q, that's what you want, equal to 1 over F, which is 1 over 10. All right, let's do some calculation because I really want to show you what is going on. So it's going to be 1 over 10 minus 1 over 40. You do the calculation a little bit. That's what you have. And then don't forget to flip over your Q is 40 over 3. All right. And now you can say, I can see it now. Your final value is positive. See that? The sign is important. The final answer is still positive numbers. So what does it mean? It means that the image is positive. What does it mean by image is positive? It means it must be real. So what you are seeing over here is, it means if I draw a diagram along with this, you place an object, okay, the focal point is here, 10, that's your focal point. And then you place an object at 40, wow, back here, right? Your object is way back. And your final image show up at 40.3. So it's about 13 something. So this is your location of the image. You guys with me? Okay, let me blow this thing up a little bit. Here we go. So you place an object right here. Okay, the focal point is at 10. Your image is right there. There you go. And it's positive. So that means your image is still in the front of the mirror. You guys with me now? Right? Anything that's gonna be real must be in front of the mirror because light can can never go behind the mirror. Mirror reflects everything. So that's what it is. But then, how can they tell if the image is upright or upside down? Okay, and what is the size of the image? Here we go. Remember the second equation? The magnification equation is negative Q over P. Okay, plug in everything that you have already calculated. Negative sign is there. Q is 40 over 3. P is 40. You take actually you have to take all the sign along with them. Right? All of these have sign associated with them. But then 40 cancel with 40. Bam, bam. What you get at the end is negative 1/3. See? So what you have over here is saying your final image is reduced down to 1/3 of the original height. So that means whatever the height of the object, the image will be only 1/3 of that. But then you look at it, I have negative sign in the front. That means it's upside down. So that's it, guys. So I can conclude the image is going to go down and 1/3 the size. Here we go. This is, maybe well, it's not that tall, but I hope you can see it. So this is your object. It's that tall. Your image is going to be 1/3 of that. And it's pointing down. Cool? All right. So this is how you use that mirror equation, guys. That's it. You only have to link between these three parameters: image location, or image distance, object distance, and the focal length. All right, try again. Part B, all right, I know how to do it now. Part B, now your object is located at 20 centimeters. So you can say your object is at plus 20 centimeters. The focal length stay the same, plus 10 centimeters. You want to figure out the Q as usual. Okay, so you do 1 over P, or actually I can just write 1 over Q equal to 1 over F minus 1 over P right away, because you know you're going to do this anyway. So that will be equal to 1 over 10 minus 1 over 20. Okay, and that's what you get is 1 over 20. So I flip it over, your Q is positive 20 centimeters. You guys with me here? All right. So what does it mean? It means your location of the image is going to appear in front of the mirror because it's still positive at 20 degrees, not at 20 centimeters. All right. What about the magnification, Ajahn? No problem. M is negative Q over P. Q is positive 20. P is positive 20. Ajahn, it's negative 1. What does it mean? It means there's no magnification, there's no reduction in size. It's going to be exact same size as the object. But negative sign means it's going to go upside down. Cool? Why? Because, well, Ajahn, it's kind of obvious. Your focal length of this one, you notice that? Yeah, the focal length is 10. But then you place your object at 20, which is exactly at your center of curvature. So of course, when you have the source at the center of curvature, once it bounces off the mirror, it will come back to itself. So that's why your image location is exactly at the same location as the object. Okay? Does that make sense? But because of the reflection, everything has to go upside down. Perfect. All right. So that's why the mirror equations take care of everything. The size of the distance and the orientation of the image. Cool. All right, guys. Last one, if you want to take a look at. All right, guys. Part C. What you have if your location of the object is at 10 centimeters. All right, I put P equal to plus 10. F stay at plus 10. And now you want to figure out the Q. Same thing, 1 over Q equal to 1 over P minus 1 over F. But wait, Ajahn, it's 0. So that means if you flip over, your Q is going to be at infinity. You guys with me? But that makes sense. Why? Because you place your object at the focal point. See that? Because when the object is exactly at 10, that is exactly the focal point. So anything that's located at a focal point will reflect the mirror and out as a parallel beam. Yeah. Because we already saw the parallel beam will focus everything down to a point. So if you have everything at that focal point, it will bounce off and give back the beam. When you give back the beam never gonna cross. They're gonna keep parallel beam forever. So that's it. That's why from this equation, it says you're not gonna get an image. The image will appear at infinity. It means you have a parallel beam out. Done. พอได้ไหมสนุกไหมอันนี้ okay it's probably not going to be fun but it's like okay it's doable. All right, very easy to apply. All right, but the good thing about this one is it's like you learn one and then you already understand two. It's like you know 2 for 1. All right, buy one get one free and stuff like that. Okay, so this is what it is. Talking about buy one get one free. The interpretation of this in Thailand is different, right? Because when you have buy one get one free mean it has to be exact same identical item, right? But อยู่เมืองไทยนี่โดนหลอกนะซื้อ1แถม1ปรากฏซื้ออะไรดีซื้อไม่รู้ซื้อข้าวแถมน้ำ You get another one. It's not the same one. It's like what? Buy one get one free. I don't get it. All right. When I say buy one get one free means this. If you replace your mirror with lens, the only difference is lens do not reflect, but it refracts. So light, instead of going backward, it's keep going because lens just let the light pass through. So see, the only thing that is going to change is this. If you have a converging lens instead of converging mirror, the light will get focused behind the lens. With me? But then with the logic that you just saw before, Ajahn, this is a real crossing of the rays. So you can do the same conclusion, Ajahn, this is real. Okay? And if you come in with a parallel beam, it's going to focus the beam down into a point at that focal point. So you can conclude, Ajahn, this must be positive. Isn't that nice? So that means when you talk about lens, you just flip everything that you learn from mirror and you flip everything to happens behind the lens. That's it. The logic stay the same. Look at this. If you have a diverging lens, it means once the light hits the lens, it's diverge out. They're never gonna cross. But same thing, if you place your eyes here, you want to take a look at it, your eyes will interpret that the rays coming from this point, but that F over there is not real. So this is going to be your virtual focal point. Okay, and the distance that you have over here is going to be negative. Done. So no difference, pretty much. Everything works just like before. Not only that, by seeing this, the equation will look exactly the same. 1 over P plus 1 over Q equal to 1 over F. No change. Everything will look exactly the same. All right. So that's kind of nice, right? Make it easy. But in reality, this is what I think is worth mentioning. When you talk about the converging lens, okay, it doesn't have to be this shape all the time, even though in the textbook, they sort of like try to draw it like this. But whenever you have the lens and have the center thickness larger than the rim's thickness, that's always a diverging lens. Converging lens. Same thing with this. You always have a diverging lens every time that the thickness at the center is smaller than the thickness at the rim. Okay. So for those of you that wearing glasses, you will notice this because if you guys are short-sighted, คนสายตาสั้นเนี่ยด้านนี้เหมือนกันเนาะ we using the diverging lens, but you never see the lens that looks like this. Right, your glasses doesn't look like this, right? It's curved in one direction. So that's why your glasses is pretty much go like this, right? It's still diverging lens, but it curved in the same direction. All right, so that's it's better for vision. It looks more natural that way. All right, so that's what it is. Now to calculate, or if you want to do the ray tracing, what I want to point out is they all look the same. But instead of having things reflected back, it just flipped to the other side because you let the light through. That's all. Okay. So that's why geometry, well, no difference. Okay. Equation wise, no difference. See, you only need these two equations one more time. That's it, guys. And we're just going to call this a thin lens equation instead of mirror equations, but they look the same. All right. Not only that, if you compare the tables, the table will look the same too, except, of course, now we understand that whatever that's going to be called positive is going to be behind the lens, because light is supposed to penetrate through the lens. And something that happens in the front that shouldn't happen, that is going to be negative. So in conclusion, the converging lens will have a positive focal length. The diverging lens will have a negative focal length. Cool. All right, let's give it a shot and see how it goes, guys. It's now it seems to be simple. All right, guys, you should be able to do this now. If not, give it a shot and see how things go. An object is located at 20 centimeters to the left of a diverging lens. Very cool. It's a diverging lens. So in your head, it goes like this, something like that. So your focal length is given here. So in your head, it's supposed to be negative 32 centimeters. You guys with me? Okay, because it's a diverging lens. Light supposed to diverge. So they were going to cross on the back. Everything is virtual, it's negative. Find the location, magnification of the image. Go. Here we go. Objects located at 20 centimeters. So what you have is P is positive 20. Okay, when you have a single device, object is always having a positive distance all the time. Focal length, you already determined is negative 32 centimeters. So this is the one that you want, the image distance. So from here, 1 over Q equal to 1 over F minus 1 over P. 1 over negative 32 minus 1 over 20. Here we go. All right, now it starts to have fun here because the final answer will have a negative value now. So I can just do simply, I put them in a product form first. So it's going to be, am I right here? 52. There you go. With the negative sign. All right, let's just leave it like that. Don't want to punch the calculator just yet. All right, and I have to flip over one more time. Don't forget, because what you have right here is the 1 over Q. So your Q is negative 32 times 20 over 52. That's it. What does the negative sign mean? It means if I draw the diagram a little bit here. Here we go. All right. I have focal length right here, 32. But then you decided to place an image, place an object at 20 centimeters right here. This is your object. And your answer gives you a negative value. So that means your image location will be on this side. You guys with me? In the front. Okay, because it's negative. So it's mean, all right, then light's supposed to, go the place where it's not supposed to go, which is in the front. The stuff that is real is supposed to be happens behind the lens. So if you approximate, this one is about 12 ได้ไหม? Approximately, is that right? ได้เนาะ? Somewhere around there. Okay, so let's say that Q is about 12 while your object location is at 20. So that means your image is supposed to show up somewhere here at the X location. With me? All right. So one more time, your object distance is positive in front of the lens. Once you get the Q is negative. So it means it's still in the front. It's a virtual one. And the distance is only 12, somewhere pretty close right here. Okay. But then you want to know what time. So is it a magnified, reduced in size? Is it upright or inverted? Now you start using the second equation. M equal to negative Q over P. So negative Q, don't forget to bring in everything, including the sign. Very good. Divided by the object location 20. All right, the good thing about this one is I can just cancel 20 out. And at the final answer is positive 32 over 52, something like that. All right. But at the end, as you can see, I got the magnification to be here, less than 1. right? The magnitude of it is less than 1. So at least your size is going to be reduced. Okay, the image will be reduction in size, but you have a positive sign in it. So that means your final image will be upright, still pointing up. So that's it. I can say, all right, it's reduced a little bit, not too much, but it's still upright. So that is your image location. Perfect. Here we go. Done. All right. So as you can see, the applications of either the mirror or lens, they are exactly the same. Equation looks the same. There are two equations that you want to use. The sign, the only logic that I'm introducing over here is wherever is positive, that's actually wherever the light that can go. Okay. For example, in this case, if the lens light supposed to enter the glass or whatever the lens material, and then it's just going to refract to the backside. So what happens is going to be real. It's supposed to happen on the back side of the lens. Anything that go negative must happen in the front where the light cannot go anymore. Okay, so the vice versa apply to, of course, the mirror. The mirror is supposed to have everything reflected. So anything that negative is going to happen in the front. I'm sorry, in the back, like that. All right. So with this, I think it's a very cool, sort of like easy to grab and go pretty much, and you learn one thing, both, right, at the same time. Very nice. All right, guys, the last question to ask, Jan, when are we going to have a negative object distance? Do you think? Is it possible to have negative object distance? As long as you have only a single device, either mirror or lens, you're never going to have a negative object distance, right? The negative object distance could occur when you have multiple devices. For example, like this. Here we go, guys. So this is going to be the hardest one, but it's not that hard. But this is, can you guess what this is? Can you guess? This is your microscope, right? You have two lenses now. You can place lens number 1 close to the object. The object is right here. It's a pencil with the tip down. And then you can call this like an eyepiece or something, the second lens. Yeah. So with this, the logic of the calculation is simple. You just put that equation back to back. So what I'm saying over here is this. You do the calculation on the lens number 1. You have an object placing here. You can use that equation, the mirror equation or lens equation, to calculate the image from the first lens, right? So here we go. This is the image from the first lens right here. Then you use this image to be the object for the second lens. And then you redo that equation one more time. Then you get the final image generated from this image from the first lens. And if you have like multiple lenses going crazy, you just keep doing this multiple times and then you're done. Okay? And the magnification equation works as well. The M is just like keep going, keep going. So that's why the conclusion is simple. You just do that mirror or lens equation multiple times, and your total magnification is simply M from each lenses or whatever mirrors multiplied. That's it. Because it's a magnification on top of magnification on top of magnification. So all you have to calculate is just M1, M2, M3, M4, and just multiply them all. Cool? All right. And this is the chance that you might be able to get a negative object distance. Can you see this? If you look at this carefully, it might be the case where your lens number 2 is being placed here. Can you imagine that? If you place your second lens right here, can you see that your image from the first lens shows up here, right? But then when you want to take this as an object for the second lens, now your objects go behind. Yeah, because you already say, hey, that's the front side of it. That's the only time that you will have a negative object distance. Okay. But if you have only single device, either lens or mirror, you're never going to get anything negative from the object, of course. All right, cool. That's kind of nice. And this is a very good conclusion of this. And I think in the exam, this is going to be the most complicated problems that you ever face, I think. Right? I'm not going to go with like a 3, 4, 5 lenses, and because it doesn't really do anything more. It's just this. But I think if you can solve this problem, I think we're done. I think that's more than enough for you to understand. All right, guys. Last question of the day. And I think this have a very good, application as well. But in reality, if you notice like lens in your smartphone, it's like a bunch of lenses, right? When they do the advertisement, right? When they สปิดออกมาแบบ20มันไม่เวอร์นะอาจจะ12เลนส์นะ combine in one. That's not just the purpose of focusing the image, but there are a lot of stuff that you have to do the correction. Okay, we'll discuss this, along the way, okay, if you have any question further. But for now, in terms of finding out the location, this equation seems to be okay, roughly. But in reality, okay, on passing, what we learn over here doesn't give you a perfect image. So if you want a really good image, you need a really good system of lenses. Okay, that's the whole point. So that's why it takes maybe a couple of years for Samsung and iPhone to perfect their camera and all the stuff, right? Right now, the camera system, it's very good, right? But if you compare this thing back like 5 years ago, it's not this great because they improved this and that here and there, correcting all the errors along the way. There are many technical stuff that need to throw into this one. But for us, we care only location, so it's kind of easy. All right, guys, try this one and see how it goes. You have 2 lenses now. It's supposed to be lenses, not 2 lenses. Lenses. Okay, here we go. You have 2 lenses and separated by a distance of 40 centimeter. And I use in combination, of course. The focal length of the first one is 10 and the second one is 12. And because they both, as you can see, is the converting lens, you can put positive sign on both if you want. Just put a note on it. Just remind yourself that this is positive. Now the object of 4 centimeter high, so you have like maybe a pencil, is placed at 15 centimeter. So that is your P. That's your image location in front of the first lens, which is, we can use number 1 for that. Find intermediate and final image distances. What is going to be the total magnification? When they have the adjective transverse, that means they just want to talk about the height. Yeah, the height. And what is the final height of the image? All right, guys. So I think this is good. So let's start from the first lens. So because we know the object is being placed 15 centimeter in front of the first lens, what I can do is I can put the subscript here, P1. Okay, because that is the object location for the lens number 1. So at lens 1, okay, lens number 1 here, P1 is positive 15. F1 is positive 10. You want to figure out the Q1 with me? All right, so you apply lens equation once. Your Q is going to be 1 over F minus 1 over P. It's going to be 1 over 10 minus 1 over 15. Very good. So far, so good. And I can work out the number a little bit. This one gives me 5 over 150. So my Q is positive 30 centimeter. With me, guys? Okay, cool. So what does it mean? It means going through this one. All right, let me put subscript 1, 1, 1, 1. Just by considering this lens number 1 alone, the objects, which is right here, will generate an image right here at 30 centimeter. All right, and it must be behind the lens because you get a positive 30 out. So that's it. That's the location of your first image. Okay, cool. But then, because you know that the separation between these 2 lenses are 40. So that means, well, oh, Ajahn, there is a 10 centimeter left right here. Okay, and that will be used as your object location for the second lens. Let me call this P sub 2. Yeah, nice. All right, so that's it. But okay, Ajahn, if this is done for the lens number 1, let's move on. Lens number 2. Your object distance is still positive. See, is it nice? Because right now your second lens is still far behind. So that means your location of the object, which is the image from the first lens, is still positive. And your focal length of the second one is also positive. It's still converging lens and it's given to be 12. And you want to figure out your Q2. All right, let's do it again. 1 over Q2 equal to 1 over F2 minus 1 over P2. Plug in the numbers. It's going to be 12 positive, subtracting out 10 right there. Okay. Now, with this, you get your final image for the lens number 2 to be negative now. With me? All right. And is I think it's negative 60. Cool. All right. Is that my number is correct? It's negative 2 or 120. Okay. So you get a negative 60 centimeter. So what does this mean? It means, look at the second lens here. It's negative. So now the image of this one has to appear 60 centimeter in front of the lens number 2. With me? All right. So that means that number 60 will give you this distance right here. That is 60. There you go. In the front. Very cool. All right. And now what is going to be your final image, or I mean intermediate if you want. So in the lens number 1, you can calculate. Okay, let me move this 60 centimeter away a little bit. It's kind of annoying here. All right, here we go. Q2 is 60 right here. There you go. So I can calculate M1, which is the magnification from the lens number 1, is going to be negative Q1 over P1. See that? Okay. And that is going to be negative Q. You just got to be positive 30. P is 15. So it's negative 2. What does a negative 2 means? It means just from the first lens alone, your image is going to be twice as big. And it's right side, upside down. Here we go. See that? So the figure over here seems to be very, very in scale here. This is the height of the object. Now the image is twice as tall. You know? All right. So it's higher. I mean the longer. It's higher twice because the M is 2. Then from that, you keep going. You calculate M2, it's going to be negative Q2 over P2. It's going to be negative, and now the Q2 is negative 60, P2 is 10. So you get negative, but turn positive 6. So that means the lens number 2 is 6 times magnification, right? Which makes sense. Look at this. This is your object for lens number 2. The final image of this one is 6 times. See that? But then it's still positive. What does it mean? It's upright. But then upright with respect to what? With respect to the object of itself. Because this, we treat this one as an object. Object is down here. So it's 6 times, but it still have the same orientation. So that's why it's the same orientation, 6 times larger. Cool. But then if you say, well, I want a grand total. What is the final? So I can say the M total is going to be just M1 multiplied by the M2, and that will give me total of negative 12. Can you see that? So that's very good because starting from here, that's your original object. This is your final image, is right there. And the negative sign over here is perfect. It's saying that the final image is upside down. Okay, and it's going to be 12 times relative to the original object right there. All right, so if this object is whatever the height that is given, 4 centimeter high, your final image will be 12 times that. All right, so it's going to be final height of 48, but negative sign means it's upside down. Okay, and this is what you always see from the microscope, because if you remember, if you do like a biology lab and all this stuff, your image on the microscope will go opposite to whatever you're seeing all the time because you see the flipped image over here. whatever point up is going to point down, whatever point left is going to point right. Okay, so when you put the cover slip and everything on the microscope, then when you slide your cover slide into the right side, the image will go left, on and on, something like that. All right, guys. So I hope this is easy enough today. It's kind of like, kind of happy physics in the morning, Saturday morning. No. All right, guys, but I think that's it. All right, so I think we wrapped up everything for the second module. We have oscillation, waves, sound, and optics, and that's it. We're done. No calculus, I hope. A little bit of calculus in the simple harmonic motion and waves, but other than that, algebra and geometry. Any questions? Yes.
Can you go back like
Two slides, okay. This one? Yes. Which one? Focal point here, right? This one? Because it says it's diverging lens. So when it's diverging lens means light is being diverged out. So if you trace things back, your focal point will be in the front. So anything that is in the front of the lens, we call it a virtual. It's not real. So that's why we put a negative sign in it. Make sense?
I mean that it doesn't say that it's in front of the
Right, you have to know it by yourself, by knowing that it's a diverging lens. That you have to determine by yourself. So in general, they just say, hey, it's a diverging lens with a focal point of 32, but you have to put the negative sign by yourself. Yes. All right, cool. All right, guys, thank you for sticking around. I'll see you guys on what, Thursday? Yeah. All right. Thank you.